When we're testing connectivity to a distant host, sometimes we will use ping, other times we will use traceroute if we also want to know the hop-by-hop path that those packets are taking along the way. That's what traceroute is good for. Traceroute shows the layer 3 and above hops along the way, meaning layer 3 routers or firewalls are often shown as well. You won't see switches or bridges or even service provider networks that are implementing a layer 2 VPN. You won't see any kind of bridging construct using a traceroute. You'll only see hops that are layer 3 or higher printed on the screen in a hop-by-hop fashion, and often you'll see 3 counters for each hop. And we're going to talk about all these different things related to traceroute, particularly because I want to lay the groundwork and also what traceroute looks like through service provider networks and how those things can change going through layer 3 VPNs. But first I want to get a good look and a good understanding at what plain old vanilla traceroute is and how it functions. For those of you who have been watching, I appreciate you subscribing, showing your interest, and that kind of gives me the motivation to keep producing content that we can all benefit from. I'd like to show you that in the few months that I've had my channel going, we've gone from 0 subscribers up to 217. So if you're new here, go ahead and subscribe and turn on your notifications so that you know about new videos whenever I post them. All right? So the diagnostic tool Traceroute is an application that is encapsulated in IP, which then is typically encapsulated in Ethernet and sent onto the wire. So you have the Traceroute application over an IP packet over Ethernet and sent out onto the network to do its job. The application layer can come in various forms and fashions, depending on the operating system or the platform that you're executing Traceroute on. You can Google it, you can look up, there's various different applications that Traceroute makes use of. In Cisco iOS, for instance, UDP is in use for the Traceroute packets. Then on Windows computers, usually it's ICMP, okay? And then, as we will see in a virtual PC and EVE-NG, you can also even make it a TCP application layer. Okay, so, but with all that said, when you're executing Traceroute, you don't know what the application layer is and you really don't care. What you care about is, can I reach the destination and what are those hops along the way? Those hops are listed in IP addresses. So there's the common thread. We don't care necessarily what the application layer is. What's common to us is that Traceroute is going over the IP layer and it's making use of something known as Ttl Decrement. It's a default behavior of every router in a network, and it's a basic function of a router. So it's very interesting that Traceroute makes use of something that every router does, Ttl Decrement. So what is TTL? Well, here in RFC 791, one of the early Internet Protocol standards put out in 1981, we see an IP version for packet header. Time to live, TTL, is one of the fields of a packet header. It is an 8-bit field, starting from bit 0 up to bit 7. You have 8 binary digits, and that's how wide the time to live is. It's 2 to the 8th power. So 2 to the 8th power equals 256. When you're counting from 0, that means you have a possible of 255 numbers. Starting with 0, you can count all the way up to 255. So 256 possible values can be in that time to live field. Before we get into Traceroute, I want to show first what routers do with TTL. I'm going to show a telnet session from router 1 over here on the far left side going to router 12 here, and I've got a little red line pointing to Fast Ethernet 01. I'm going to be telnetting to the IP address of Fast Ethernet 01, 1.1.8.2. Okay, and we're going to be going through all these routers to accomplish this TCP telnet session. I have a packet capture Wireshark running on Fast Ethernet 00 of router 1 and Fast Ethernet 01 of router 12, so we can see what this looks like. So here we go, telnet 1.1.8.2. Okay, and let's stop these sniffers and let's see what we have. If I highlight this first TCP packet, this one at the top here, frame number 57, and I open up the IP layer and I go to the TTL field, I see that the time to live is 255. If I go over here to router 12's packet sniff, over here on Fast Ethernet 01, and I open up that same TCP packet, and I open up the IP layer, I see that the time to live is 248. So we can see that Cisco iOS crafted the IP header and populated the TTL field with 255 from the onset. At the beginning of the TCP telnet session, the TTL was 255 from router 1. It went up to router 19, then to 18, then to 17, to 16, to 15, to 14, to 13, and then to 12. And we saw that by the time it got to router 12, it was 248. So the TCP session started with a TTL of 255. When it arrived at router 19, this is where the TTL decrement occurs. When a router receives an IP packet, it looks in the TTL field and it decrements it by 1. So that packet is decremented as it crosses router 19 and ends up being 254. Crosses router 18, it's 253. Crosses router 17, it's 252. Crosses router 16, it's 251. Crosses router 15, it's 250. Crosses router 14, it's 249. Crosses router 13, and when it's received at router 12 on our packet sniffer, it's 248, just like we saw. So whether it's a telnet session or a ping packet or a traceroute packet or any IP application, there's always a value that's created at the originating source of the communications. That TTL is populated with some value. I'll say this, that on some operating systems or some platforms, sometimes that TTL value starts as 64 or it starts as 128. Or in this case, we saw in Cisco iOS, particularly for telnet, it started as a 255. But as it goes through an IP network at every router hop, it's decremented. Well, the purpose of it is to keep packets from floating or being forwarded, endlessly around an IP network. So a packet can never go further than 255 hops. Okay? And that's because the value is, as we saw in the header, is only 8 bits wide, and the highest number it can start at is 255. And if it's decremented at every router hop, every time a router receives it, then it can never go beyond 255 hops. Well, why is that? Because when the value is 0, it is dropped. I'll show you that in the RFC. Sorry about that, I cut myself off. I was saying that I will show you in the RFC what happens when the time to live reaches 0. This field indicates the maximum time the datagram is allowed to remain in the internet system. If this field contains the value of 0, then the datagram must be destroyed. Okay? So, as that TTL value is set to 255, and we saw it forwarded across several router hops and decremented at each hop, when it gets to a router that receives that packet, and if it's a TTL1, when that router receives it and it decrements that 1 to a 0, it drops that packet and destroys it. And I'll also tell you, it sends back an ICMP message to the originator of that packet. It sends back a message that says TTL expired in transit. And this brings me to what Traceroute does in making use of this behavior in routers and the TTL expiration. And so what the Traceroute utility does when executing here on this Traceroute source, this is where you want to execute the Traceroute command, and you're tracing to a destination out here in the cloud. When those packets leave this source, the IP header is set to TTL1. And so what do we know about when a router receives an IP packet? It decrements the TTL. Okay, so this first packet is received at this router, -1 on the TTL equals 0. And we also now know that when a TTL is decremented to 0, the packet is dropped, and the device dropping the packet sends back a TTL expired in transit message. So this router sends back TTL EXP, I'll just put an X, expired in transit. You probably can't read that, but it sends back a TTL expired in transit message. Now, on the screen of this computer or router, you see this IP address because when this packet comes back, you see the source of that TTL expired in transit message. That's how you know what the IP address is of that first hop. So if you executed traceroute on the command line here, and you get a 1.1.1.2, 5 milliseconds, well, this IP address is the IP of the interface on this first hop router that originated this TTL expired in transit message. And this is how long it took to get it back. Let's just say a couple milliseconds. Well, we do know that there's a couple other millisecond measurements for this first hop that we normally see on a traceroute. You usually get 3 measurements. That's because this transaction happens 3 times at every hop. So again, we send out a TTL of 1. We get back, so the router does its job, it decrements the TTL to 0, sends back a TTL expired in transit, and it took another few milliseconds to get that second response back. It does this again. TTL1, router decrements it to 0, sends back a TTL expired in transit, and there you have it. There's your third measurement for that first hop. Now, I will say this, that you can turn off the amount of probes. These are known as probes. And I'll show you how to do that, where you can limit it to only 1. So at every hop, it only probes 1 time. Making traceroute a little simpler, it's still the same underlying concepts. It just only probes it once per hop. So taking this to the next step, what traceroute is doing is it's going to increment the TTL field of the originating packet every time it executes the next hop. So as we just talked about, traceroute starts off. You plug in the destination IP, 199.199.199.2 is the IP address out here. Okay, that's the destination. First hop, the first packet goes out, TTL1, the first hop router decrements it to 0, sends back a TTL expired in transit. You get that measurement, does that 3 times. We already talked about that. The next packet that goes out is set to a TTL of 2. So this packet goes out, TTL2, this router gets it, -1, that packet is set, is now a value, it continues on, its TTL is set to 1. After it gets decremented from that first hop, it is now a 1. It is received at this second router, it decrements it by 1, which now equals 0. And what do we know about a router that decrements it to 0? It sends back a TTL expired in transit message, and now we have our next hop with the millisecond measurement on our screen. Again, it does this 3 times normally, so you get 3 different measurements. And this process continues on. The next packet that goes out for this third hop router out here is going to be set to TTL3. And on it goes. All right? So looking at our test environment here, router 1 here on the left and our virtual PC 199.199.199.2 over here on the far right, if we are on a console of router 1, we will execute a traceroute. I'm also doing a packet sniff on this first hop router's fast Ethernet 0/1 interface. And so if we traceroute 199.199.199.2, let's see what we get. So there we go. There's our traceroute. And let's evaluate the packet sniff. Okay, let's look at this packet sniff. Let's scroll back up to the top. And source IP address is 1.1.1.1. We see on router 1 that is in fact our source IP. We are tracing to 199.199.199.2. That's what we were doing. And that packet goes out, and the time to live in the IP layer is set to 1, just like we talked about. Now look what we get. We get a reply from source 1.1.1.2. Look at this. Our first hop that's printed on the screen is 1.1.1.2. The message in the right above the IP layer is ICMP time to live exceeded in transit. ICMP type 11 code 0. Okay? Next packet, same thing. IP header, time to live is 1. We get a response back from 1.1.1.2. I would say that's the second response we got here. We send out the third probe. We get a third response. Time to live exceeded. There it is. And there's our third probe. Next, the UDP packet goes out with a time to live set to 2. It goes across the first hop, and we get a reply back from 1.1.2.2, which is our second hop. 1.1.2.2 with 40 millisecond timer. Sounds like a lot of milliseconds, but it's a software-based router environment, so there's a bit of latency involved. There's the next one, time to live of 1. We get a response back from that same hop. There's our millisecond measurement for the next one. We send that packet out again, time to live is set to 1. Goes to the second hop again, 1.1.2.2, and there's our third response. On and on it goes all the way to the destination. Okay, I'll show again. Time to live 3. There's the next one. There's the next one. Time to live 4. You see that? There's the next one. There's the next one. There's the next one. And we just on and on it goes. Time to live 5. 5. Focus on this right here. 5, 5, 5. I think this next one is, that one's 5 also. Then it's 6, 6, 6. Then it's 7, 7, 7, and on it goes, okay? So I'll show you how to change the probe count. Okay, so I'm going to show you how to only probe once per hop. The traceroute IP address, I put numeric so you don't get reverse DNS resolution. And probe, set it to 1. So look at that. Look how nice and clean that is. You have your millisecond measurement at each hop only once. And so let's look at this packet sniff now. Okay, let's go back up to the top of this packet sniff, and our source is 1.1.1.1. Go into our destination. In the IP header, our TTL is 1. We get a response back from 1.1.1.2. That's that first hop. And it is TTL exceeded in transit. I've been saying expired, but it's exceeded in transit. So I guess that's the same thing. Your TTL has expired. Now Next hop, TTL is 1. We get a response from 1.1.2.2. There it is. Next hop, TTL is 3. We get a response back from 1.1.3.2. And on it goes. So as we progress through the traceroute, you get 1.1.4.2, then 1.1.5.2, then 1.1.6.2, 7.2, 8.2, 9.2, 10.2, 11.2. Then we get down to our destination. We send out a trace packet, which is that UDP packet. Again, Cisco iOS uses UDP as the application layer. That time to live is 12, because it's our 12th probe. It arrives at the actual destination, 199, 199.2, and we get a response back. But under the hood, look what the response is. Up to this point, it's always been time to live exceeded, 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 TTL exceeded, TTL exceeded, TTL exceeded. Except from the actual destination, we get a destination unreachable message. Destination unreachable, port unreachable. So let's look at that. When you look in the IP layer, you have ICMP, but it's no longer a time to live exceeded. It's a ICMP type 3 code 3. Destination unreachable, particularly port unreachable. So it's referring to the UDP packet and that port number in the UDP packet for the destination. The destination is telling us, hey, I don't have a port listening at the UDP layer, so that port is unreachable. Well, that's okay. The Traceroute utility interprets that as a response, and it tells us how long it took to come back. But I just wanted to draw your attention to the fact that that last hop is not a time to live exceeded in transit. It is no longer in transit. It has actually reached the final destination, but now it's actually a port unreachable message related to the UDP message that was originally sent to it. All right? Now, interestingly, if we go to the virtual PC that's on the far right side over here, 199, 199, 199.2, and we do the same, except going back towards the router itself. By the way, you have to set the TTL to something greater than the default value in this virtual PC, or you only get 8 hops. You won't get to the destination. So let's set it to something higher, and let's see what happens. So there we go. We trace all the way back towards router 1, which is 1.1.1.1. And in this case, we actually get on the screen the type 3 code 3 destination port unreachable message. So I just wanted to show you that here we are. We have 2 different operating systems, Cisco iOS and also the virtual PC built into EVE-NG. And that last message is actually shown in detail that it is in fact an ICMP type 3 code 3 on the virtual PC. I did mention that I was going to show Traceroute using TCP as an application. On the virtual PC over here, you see that Trace can use a few different protocols. You can set the protocol number as 1 for ICMP, 17 for UDP, which is the default, by the way, that we saw earlier, or we will see. And you can set it to 6 if you want it to be TCP. So let's do that. Let's trace across that network to router 1, and we will change it to be TCP. And again, we have to set the max TTL to be something greater than the default of 8, or we'll never make it across this network more than 8 hops. We'd get about as far as router 16, and then we wouldn't get any further. Okay, so let's do this. I'm running a sniffer here. What did I do wrong? Capital P. Oops, excuse me. Okay, here we go. Capital P. There we go. And let's look at this sniffer. And we go up to the top and we see that coming from our IP address is in fact transmission control protocol, source port, destination port. It just chooses some random port that this application uses here. And the IP layer is set to TTL1 on that first hop. We get what we would expect, a time to live exceeded in transit message, and we move on to the next hop. And on it goes. So let's go to the next one. Okay, of course we're getting 3 probes per hop, so that's the second probe for the first hop, third probe for the first hop. This would be the first probe for the second hop, and there we go. That is Traceroute using TCP. I'm curious, when we get down to the final destination, we get a TCP, looks like it's a reset. We get a TCP reset on the final hop, which is good enough to print a result and a millisecond rating for each one of those 3 probes on that last hop. Hey, I hope that helps you understand more of basic router functions in a network and what Traceroute does to leverage those basic functions like decrementing TTL so that you can see the hops you go through a network. All right? So hey, if you like what you're getting from this channel, go ahead and subscribe, turn on your notifications so that you know when I drop new videos. I enjoyed it and I look forward to the next time.